Yeah. Oh yeah.
It has been lost.
Okay.
All right. Well, let's get started. I'm sure there'll be some people still filtering in, but it's great to see so many of you back here for the first forum for AI of the 2023-2024 year. I'm Peter Stone, faculty here for the past 20 years or so. And it's my very great pleasure to introduce Dr. Brad Knox, who is a research scientist here, is also an alum from UT Austin. In 2012, got his PhD. The thesis was learning from human generated reward, learning from human generated reward. Really a pioneer in the space of reinforcement learning from human feedback, as it has come to be known, but arguably wrote the first PhD thesis that addressed that topic back in. There was a paper in 2008 that introduced that concept, and then it was the feature of his PhD thesis in 2012. Since then, he's gone off and he started a company that used reinforcement learning from human feedback in a toy called Bots Alive. He's been a research scientist at Bosch, at Google, and recently is back here as a research scientist at UT Austin. We're very fortunate to have him, and he's going to tell us now about all his research passion on reinforcement learning and alignment for AI. So take it away, Brad.
Thanks so much, Peter. Thank you. I'm glad to be here. I'm going to be talking about models of human preference for learning in sequential tasks. And first, I want to just give a very high-level motivation for alignment. This talk is going to be concerned with aligned reward, meaning that the reward, when you add it up to return and then make expected return, that basically the reward orders policies in ways that are similar to how human stakeholders would order them. So basically, the reward represents human interest. So a couple of just kind of cartoonish examples here. HAL in 2001 Space Odyssey has an objective. It's not exactly a reward function, but it's an objective. And that objective leads it to try to murder all the astronauts because it sees them as an obstacle to achieving that objective. And then here there's a drawbridge that presumably is going up, and a car is jumping over it. This is from the Blues Brothers movie. And I imagine that none of us, if we were in an autonomous vehicle, would want to save some time by trying this out. However, in a paper in artificial intelligence that I won't talk about again, we looked at reward functions that were published for autonomous driving and found that most of them would embrace behavior like this, making some progress at heavy risk. Yes?
Were these papers primarily industry papers
or they were research papers. So we just took them from top venues like ICML, AAAI, and then some of the top ones that were focused on autonomous driving. But this is just an illustrated example. And the idea here is that as the capabilities of artificial intelligence systems increase, it's going to become more and more important that we can align their objectives to what our interests are. And when we frame the AI problem as reinforcement learning, that means designing the reward function and the discounting in a way that is aligned. So here's my recent research on the topic. I have a couple of papers on manual reward design. By manual, I mean just the way that we actually create reward functions in practice most of the time, where we maybe write some things down on paper and eventually just code it up. If you're interested in that topic, I definitely recommend those papers. And then we have work on inferring reward functions from human input. And I'm going to talk about, in this talk, I'm going to talk about the latest two papers. So first, let me try to give an intuition for what I mean by a model of human preference by using, again, a cartoonish example here. So we're going to talk about a model of human head motion. And let's say there's going to be a service proposal. And the question will be, is the service desired? And the model of my head motion is that if I go like this, I'm answering yes. And if I go like this, I'm answering no. So that's pretty typical for at least U.S. society. So maybe for some reason, I think when I wrote these, I was thinking about help from grandparents when you're busy as a parent. My mother-in-law actually has done this for us. Would you like me to take your car for an oil change? And so I'm shaking my head. And so by this model, the answer is no. Should I take your child swimming? And if I go up and down, the answer is yes. However, if you're in Bulgaria, and there's some subtlety that I'm skirting over here, but if you're in Bulgaria, the meaning of these gestures is reversed. So if your model is inappropriate, you can end up somewhat dangerously taking a child that's dangerous around a pool when the parent said no, because you're using a model of human head motion to infer the hidden state of the human that led them to make a certain reaction. And so if the model is wrong, you can infer the wrong hidden state in the human and misunderstand what the human wants. So this is just a very high level intuitive example, but really this is going to be about models of human preference in this way, even though that wasn't preferences. So the takeaways for this talk, I just want to kind of put them forward to kind of prime you. If you walk away with nothing else, I hope that you'll remember one, that in the body of work on if there's some chairs here, feel free to grab them and come sit down. That in this body of work, a key part of the current model of what drives human preferences in sequential tasks is unstudied and unvalidated. And hopefully you'll walk away thinking that it's important that it is validated. We propose regret as an improved preference model, and regret at a high level can be thought of as something that measures a segment's deviation, a trajectory segment's deviation from optimality. And then just even higher level, I hope that you'll walk away thinking that the model of human preference is a critical piece for alignment. It is part of the algorithm that really does need to be looked at.
I thought the takeaway was just don't deploy the AI in Bulgaria.
All right, so let me kind of link this to some other fields. Here we've got a reward function. For simplicity, I left out the discount factor. And we add a reward in reinforcement learning to return, which could be considered its own function. This notation won't come back. But reward can equivalently be thought of as -1 times cost, or this return that is added up to has all of these either synonyms or very related concepts in other fields. And one particularly a note is utility and expected utility theory. Okay, let's look at what this learning problem really looks like. So let's say that we have a grid world here, a very simple grid world. And let's say that the purpose is for the agent to get to the goal as fast as possible. And I'm keeping that a little loose here. But so take a look, think for yourself if you have a preference over the two. I hope, maybe some people disagree, but I hope that we all would prefer this one because I'm going to use that as an intuition for a lot of what's going to follow. But let's set that aside and think about just the method in general. So what's done is that process happens over and over with different pairs of trajectory segments. They could be full trajectories that go to termination, but they could be just segments. And from that, you get these pairs of segments that each have preference labels, and that's your preferences data set. And here's the algorithm. So you're going to optimize the reward function, and any learned reward function I have a hat over. And you're going to optimize it so that you're maximizing the likelihood of a preferences data set. That's too bad it's washed out. And the key part here is that the likelihood of each preference is based on this preference model, where this can be read as the preference or the probability of segment 1 being preferred over segment 2, given the learned reward function. And this preference model can be defined in different ways, given these two segments in the reward function. And that's what we're going to be focusing on.
Question here?
Yeah.
Is there an element with this that takes into account, as you were mentioning when we're in a different cultural context, how maybe what we want our model to learn differs? Is there a way to model that?
That's just repeating the question for people on Zoom.
Yeah, so the question is would part of this incorporate different cultural preferences? Yeah. So I think it does inherently, in the sense that we're trying to take people's preferences, which might be different in one culture or another, and learn a reward function from them. The question of how you might, in a deployed product, have one single reward function that works for everyone, or mix people's preferences to create one reward function. Just all these like social choice problems. That's very important, but it's not something that I yet have a ton of expertise on, and it's not the focus of the talk. But I think that's a very important topic. Okay, so why preferences? Why is this a worthwhile problem to pay attention to? One, it's now an established technique in reward learning, and it's incredibly established in expected utility theory. It's fairly intuitive for humans to say, I prefer this over this. And also, for people who are familiar with my past work on the Tamer framework, people were giving what we interpret as numeric feedback, which you might think of as like Likert scale feedback. And these pairwise preferences remove a calibration issue that can be difficult there. Judgment might be easier than control. So if you're comparing it to imitation learning, giving demonstrations could be more difficult than just saying this one is better than this one. And I think that actually links to, at least my speculation is that links to why the last fine-tuning step for LLMs is to use preferences and not the demonstrations from the previous fine-tuning step. And then, yeah, I already mentioned it connects to expected utility theory. And then we'll see that in ideal settings with our preference model, the reward function that underlies the preferences data set can be recovered. A little bit of notation here. So I'm going to be talking about segments, and I've already said a sigma here is a segment. And this is the way we show the length of a segment, which is the number of transitions. And for the first half of this talk, which basically this talk is 2 papers. So for the first half, the first paper, we're going to assume a segment length of 3. And then also, here's that same segment broken into the 3 transitions. And this is how we denote the state, action, and next state for each of those transitions. So just taking this one because I can reach it. It's the segment and then the time index for the state and the action. Oh, and then also the final state is designated by the same notation as the segment length. So this work, this body of work really got launched by Paul Cristiano et al. There's definitely earlier work, but in the deep learning area, this really popularized it. And to my understanding, it's the first work to look at a deep representation of a reward function that's learned from preferences. And they showed impressive results on Mujoko and Atari. And since then, there's results in robotic manipulation, autonomous driving. And then also, as I'll get to at the very end of the talk, this methodology, a very specific form of it, is being used to fine-tune large language models like ChatGPT, Llama 2, Sparrow, and a lot of the most well-known language models. There's a lot of, this is just selected related work, and I've arranged it to kind of show where the related work focuses on in the algorithm. So there's work on active learning. Basically, what segment pairs do you want to put in front of people for preferences? There's the work by Paul Cristiano on the representation reward function. There's work that includes demonstrations as well. And there's a lot of really great and influential and impactful work in this area. But until the work that I'm going to talk about, there's no focus on this preference model. My guess is because that is the part that connects to the human. And I think we computer scientists often prefer to start with an axiom for the human and then work on the problem as it's defined by that axiom. But this is an important part, as we will see. And that's, again, what we're going to focus on. So that brings me to the first topic, the specific content for the first paper. And this is work that I did as a joint first author with Stefan Hackes-Kessel, and then also with Serena Booth, Scott Neekum, Peter Stone, and Alessandro Aliavi. And a lot of this, for this paper, this work, was funded in part by Bosch. I was working at Bosch when I started this work. All right, so the outline for the remainder of this talk is I'm going to introduce preference models, the dominant one and our proposed one, talk about identifiability theory, and then talk about some empirical results with each of these preference models. And then in the second half, I'm going to ask what happens when our proposed model is what drives preferences, but the dominant model is assumed. So basically asking, well, if we're right that we have a better model, why is it that all these recent works have such good performance? Okay, so models of human preference. We're going to stick within this family, which is a generalization of the dominant model, which I'll describe in a second, which is the probability of segment 1 being preferred over segment 2, is this Boltzmann distribution, where the input is what we're calling a segment statistic, basically the segment input to some function f. And we assume a temperature of 1 because you can just scale the output of f to have the same effect as changing the Boltzmann temperature. And I prefer the simpler way of expressing it, where it's the probability is the logistic of the difference of these segment statistics. So for those who could use a quick review of logistic functions, here's a logistic function, and the x-axis would be the difference in the segment statistics. So if segment 1 has a higher statistic, then it's going to be above 0, and so the probability of referring segment 1 is going to be above 0.5. Okay, so the missing piece here, we want to define this preference model. And the dominant model does not have a name. We named it. I don't think it had a name because it was so dominant that people didn't need to have a signifier for the model. They just assumed it. We call it partial return. And it's just the discounted sum of reward in a segment. So this. I'm repeating myself a bit, but this is assumed by all the related work that I've talked about so far and a lot of other work.
Sorry, can this
Yes.
way of doing things be derived from some underlying probabilistic assumption, kind of like ELO ratings in chess?
Well, I think the whole family can be considered a form of ELO ratings,
Okay.
but the specific way of calculating the segment statistic is more specific, I think, than whether it's considered an ELO rating or not.
Okay,
Does that
but
make sense?
like, can we assume that that there's some Gaussian distribution around the actual preference or something? Or
Off the top of my head, I don't know.
Okay,
But
fine.
if there was an answer yes to that, I'd be very interested.
All right, thanks.
Okay, so let's bring back that example from before, and let's ground it out a little bit more. I said the purpose was to get to the goal as fast as possible. So an aligned reward function, the most canonical one would be just to give a time penalty of -1 for every step until the goal is reached. And we'll also, since it's an episodic task, we'll assume that there's no discounting. So in this case, the partial return is -1 plus -1 for that one, so -2. And -1 plus -1 for this one, so -2. So in this case, the partial return preference model is indifferent between these two segments. Even though I hope we almost all agree that this one, by our gut, is actually preferable. So what seems off here? One way to put it is that there's a different end state, and the value of the end state is better over here than the value of the end state over here, and that's not part of the partial return preference model. You could also look at it in terms of decision optimality. These are optimal actions, and these are suboptimal actions. And that is also not directly considered by the partial return preference model. So in-state decision optimality. So let's look at another example. Here, the partial return again is the same, so it's indifferent. But now the end state's the same. What's different is the start state. And so in this case, maybe I should give you a little bit of time to think about it. But I think, again, people are going to tend to prefer the one on the right, because this one is squandering a good start state. So it has a higher opportunity cost. So maybe the start state matters too, that if some segment starts in a better situation and doesn't achieve more because of starting in that better situation, that's going to factor into people's preferences. So here I'm just summarizing what I just said. Humans intuitively appear to consider state value and decision quality, specifically the start and end state, and the partial return preference model does not. So let's try to address these concerns with a new preference model. We call it regret, and the segment statistic here is going to be negative regret. These negatives can get a little confusing, but it's going to be negative regret of a segment. And as I said before, the high level idea, I'll get into math in a second, but the high level idea is the regret measures the segment's deviation from optimal decision making. So the regret of an optimal, a segment full of optimal action is going to be 0, and then any suboptimality is going to push the regret above 0. Okay, we'll focus first on when all transitions are deterministic and then relax that assumption. And what we define regret of a segment to be is the regret of each transition And I won't go into exactly how we define that, but what that resolves to is this equation here. So what that is first, this is my shorthand for partial return. So the partial return preference model, this is all it looks at. So that is included in this regret preference model. And then also we have the end state value. So this is the best possible expected return from the end of the segment. And together, these make the best possible expected return from the start state when you assume the segment is what happens from the start state. We also have the start state value. And so you can think of this as the best possible expected return from the start state before the segment is taken. And so really this ends up capturing opportunity cost, except it's negative because we're going to stick it in there with a negative sign. But basically this difference is at the start state was the expected return that the optimal policy could have gotten, but compared to what is the expected return after you force the segment to happen, and then you look at the expected return from that end state. So this is kind of a key slide. I'm happy to stop and take questions here if there's any like clarification I could do. Yeah.
So I guess sort of the assumption here is that humans are like good at judging the, best possible, like the value, the optimal value function, right?
Not necessarily that people are good at it, but but putting it in there makes a better model of, so there's a little bit of nuance here, but it makes a better model of their preferences than without it. So having the optimal state values in here doesn't mean that we're saying people can calculate optimal state values. All we're saying is that this model ends up predicting people's preferences better than not having them in there.
So is it safer to say it's the right-hand term is the best the person thinks you could do from the end state, and the first term is the best the person thinks you could do from the start state?
Yeah, that's right.
Sorry, can you
Yes, Trudy?
explain the notation a little bit? So the S sigma comma 0 is the comma.
Yes.
0. What's going on there?
Thank you. I forgot to mention that. So let's see, there's a few things in here. This D here is because we're assuming deterministic transitions. That'll go away soon. Remember, this is the length of the segment. For R, I have 3 types of R's. With R with nothing is the ground truth R, like it's the real reward function. R with a hat is a learned R. And then I use a tilde to just mean any kind of reward function. So it could be learned, it could be ground truth. So you'll mostly see tilde to allow general expressions. I think it, yeah, anyway, so let's see what else. So here, as I mentioned a number of slides ago, so this is the state for this segment at time 0. And this is the value function, the optimal value function for this reward function, R tilde. And then similarly, the optimal value function for the reward function R tilde at the end state, which is basically it's signified by the sigma and then the segment length notation. This won't come up too many times. I agree, it's a bit of a lot. But it's hard to, I've tried to pull it out and get rid of it, but I haven't succeeded yet.
So it's actually, you could actually rearrange that, and essentially all you're doing is optimal reward start point minus the final, and you compare that to like the accumulated reward over the trajectory. That's all you're doing. Yes.
I think so, yeah.
Okay.
Just see if I understand, like at the end of the day, what you're gonna be doing is like training a neural net to, compute an R that sort of optimizes when you plug it into this formula, to do as good a job as possible at predicting which sigma 1s are rated higher than which sigma 2s.
Right. Yeah.
Do you already know V-star, or is V-star something you find out?
Yeah, so I'll get to that. That's a really good question. That'll come up.
Is the discount just being left out for simplicity, or is it incorporated in this?
Oh yeah, thank you. When the discount is not in here, then I'm removing it for simplicity.
Okay, but
Because we don't really get into discounting much unless there's a couple places where I explicitly talk about it.
Yeah,
Gary?
maybe relating to something that how important is it that you start with the optimal policy? Could it be
VSTAR gives us a specific policy to.
Could I define a family of regret if you define it here for any?
I think you probably could if you had like a strong motivation for some other policy. The theoretical consequences of having it be the optimal policy are desirable, though.
It's a model for humans.
Exactly. So yeah. So there. I probably should move on after this question. But there's questions of what's a good normative model, like what would you want humans to follow if you could choose, and then there's what's a good descriptive model, which is what do they actually follow. But there's also, you can have prescriptive methods where you find ways to push people towards one model or another. So it's worthwhile to look at the theoretical properties, the normative properties of these models, so that you can then say, well, descriptively, this is a pretty good model. Normatively, it's a really great model. So can we train people and design the interface to push them to follow this model even more? Okay, we probably should, well, we can keep questions. I might have to have questions held till the end if we keep having a lot of questions, which is generally great. Okay, so I said we were focusing for now on transitions being deterministic. And so far, one of the nice properties of this is that, like I said before, with deterministic transitions, this regret will always be 0 for optimal segments with optimal behavior, and it will always be positive for segments with suboptimal behavior. And so it separates optimal behavior from suboptimal behavior. And this is going to be important for a number of reasons. However, when you have stochastic transitions, that's not the case anymore. So let's look at this simple lottery. There's a safe action, which always gets 0 reward. There's a risky action, which half the time wins, half the time loses. And the rewards are -10 or 9. And so the expected value here is negative. And what that does is, here the optimal decision, the best decision is to not play the lottery, to take the safe action, but the best outcome is to win. It looks like I accidentally changed the reward there, but the point stays the same. So now we have this question: do we want our model to say that people prefer better decisions or better outcomes when those disagree, like in this lottery situation? And I think both actually end up being a fairly good model, but we chose to focus on the one that assumes people make the best decision, so that's still separating optimal from suboptimal behavior. So here's the model with stochastic transitions. So it's the general version, and that's just it's the discounted sum of what's called the optimal advantage of every transition, every state action pair in the segment. So if there's 3 transitions, each transition has an optimal advantage, and then you're going to add that together. For those who are not familiar with optimal advantage, this is how it's defined. It's the optimal Q value minus the optimal state value. And basically, it's going to be 0 if you take an optimal action. Even if you have an unlucky outcome, it's going to be 0. And then it's going to be negative if you take a suboptimal action. And a characteristic of it that will come back is that the maximum optimal advantage at any state is going to be 0. So any optimal action will get a 0, like I said. So this is the core, like this is the kind of the kernel, the easier to remember for people who are familiar with optimal advantage, at least easier way to remember what the regret preference model is. It's just the sum of optimal advantages. All right, we're going to look at our examples here again. So on the right, we have optimal behavior. So the sum of these optimal advantages is going to be 0 and 0. And then on the left is suboptimal behavior. I can't remember off the top of my head what the optimal advantages actually are. My guess is -2 and -2, but it's negative. So it will tend to prefer, it'll have a higher probability of preferring the one on the right. The second example, where the start state was different, same thing. There's optimal behavior versus suboptimal behavior. So this will have a regret of 0. This will have a positive regret, which is a negative advantage. So again, it'll agree with what I hope is all of our intuitive preference. So this regret preference model might seem esoteric or, like that, that there's a million different options and this is just one option. I think there are some other good options, but it actually has some strong precedent. So looking at inverse reinforcement learning, it's often assumed that demonstrations are noisily optimal for inverse reinforcement learning. And what we're assuming is that preferences are noisily, people noisily prefer optimal segments over suboptimal segments. So there's a strong analogy there. And again, it's Boltzmann rational with respect to our A star. And for reasons I won't go into, Q star wouldn't allow for this property of noisily preferring optimal segments. The main downside, going back to your question, which I'll come back to very briefly, is that like inverse reinforcement learning, if you want to learn a reward function with a regret preference model, it appears to require solving a Markov decision process in the inner loop. And for modern methods, doing it in a way that we can get a gradient as well, or at least approximating that. So we're going to approximate it because solving it is not actually tractable. Yeah.
Isn't that pretty difficult to do? Or is it somewhat standard?
It is difficult. I'm not an expert in inverse reinforcement learning, but that's a very healthy, growing field despite that weakness for inverse reinforcement learning. So that's one thing that gives me courage. We have one approximation technique that we have working in simple tasks so far, but also later in the talk. Oh, go ahead.
Rephrase my question. Isn't it good that the second step can be usually successful only when you have a good simulator in that? And then you don't have a good simulator, it's very fun. Isn't that true?
I don't know all the different ways that people handle this in inverse reinforcement learning. We end up handling it with something called successor features, which I won't have time to get into, but that does not require. Well, yeah, you might argue it requires a simulator in some way. It depends on how you.
Just for like a language model.
There
is no.
Right.
Right. So
right.
I mean, that's the basic of my question.
Yeah. So yeah, so I think it's a dilemma here. You could take a model that, at least if you believe the argument so far, a model that is easier to use but is wrong. So there might be alignment issues, but at least you have an easy computational task. Or you can take one that is a better fit for people, but it's difficult to use. And from a research perspective, it can be nice that there's some difficulty, that you have a higher potential plateau for performance, but it's harder to get there. That said, at the very end, or near the end, we'll talk about using this model without learning a reward function, and that issue goes away. All right, so for theoretical properties, we're concerned with reward identifiability, and the way we define that, and others have defined that, is given some ground truth reward function that then is fed into one of the two preference models, you then create an infinitely exhaustive preferences data set. So every segment pair has infinite preference labels. And then identifiability is the characteristic that there's some algorithm that guarantees that the reward function it learns will have an equivalent set of optimal policies to the ground truth reward function. In the paper, we prove that with regret, reward functions are identifiable. And then we have 3 different contexts in which is not identifiable with partial return. Those are in variable horizon tasks instead of fixed horizon, with segment lengths of 1, and then also without Boltzmann noise in the preference labeling. So if there's no error, which the Boltzmann noise is really meant to model error. So if they're error-free preferences, then you also lose identifiability.
So I think it's important to say like the implication of this is that if you use the partial return model, that you would learn a reward function that would give you an optimal policy that is not the optimal policy that the person had in mind when they gave the preferences. There
are cases where that's the case, even with infinite exhaustive preferences, and that's where the partial return preference model is correct. So there's really that normative case where we're saying, well, what would we want people to follow if we could choose? And so this is showing that there's limits to the partial return preference model where maybe we wouldn't want people to follow it, even if they could. I think for time, I was gonna go through one of the proofs related to the lottery, but I think I'm gonna skip it for time. And let's go into actually learning with estimated regret. So here's the algorithm that I reviewed before, and here is the regret preference model formulation, or at least this is the part that's plugged into the logistic. And as I mentioned already, the current candidate reward function, you're going to need the optimal advantage, which you can calculate with the optimal state value and action value functions. But that's very computationally expensive and not something that you would really want to do in the general case. So in the paper, we use a technique that's at this point very established called successor features to quickly estimate Q star and D star in a way that's differentiable. I could go into that in questions, but it's a bit in the weeds. Okay, so we're going to learn some reward functions. This is the way that we do the learning and then the evaluation. So we've got some ground truth reward function. It's going to be either taught in some way to a human or used for synthetic preference generation. And then we get our preferences data set. We learn a reward function. So there's R hat for learned. And then we're going to use value iteration to get usually the optimal policy. Sometimes if it's egregiously bad and never terminates, then we may not exactly model it, but the approximately optimal policy. And then we evaluate that policy according to the ground truth reward function. So this is also a way of evaluating the alignment of the learned reward function by seeing how its optimal policies do with respect to the real ground truth reward. So we're going to focus on synthetic preferences first. And this is what I just showed you, but complicated by the conditions. So we're going to create two preference data sets, one created by the partial return preference model and one created by the regret preference model. And we're actually going to do this twice, one noiselessly, so with no error. Basically, whatever has lower regret is preferred, whatever has higher partial return is preferred. And then we're going to do it stochastically, where that preference model, which is a probability distribution, is sampled. So we'll test both. We get similar results. And then for each of these preference data sets, one created by partial return, one created by regret, we're going to do reward learning with each of the two preference models and see the results. So we're going to do that in 100 randomly generated grid ruled MDPs, these relatively simple tasks. You can see the amount of these different objects varies, the proportions vary, the placement, and then also there are sets of possible reward values that we randomly choose from for encountering each of these objects. And a couple of them are terminal objects. They create terminal states. So here's our results. It's a little noisy, so I'll step through it. Or a little noisy, sure, but that means something else in the context of the talk. There's a lot going on here. So first, let's look at where each model has created its own preference set and then learns on it. So regret learns on a regret-based preference data set. Partial return learns on a partial return-based preference set. And then the solid versus dotted is just whether the preferences were generated noiselessly or stochastically, but you'll see the patterns are pretty similar. So we see that on its own preferences, regret tends to do better at various levels of training set size. And then if we change our focus, and now we're looking at the regret-based preference data set and see which of the two models performs better on the data set based on regret. And we see, maybe least surprisingly, that the regret preference model does best on its own preference data set. And then doing the same thing for the partial return preference model. If you have preferences by partial return, the partial return preference model does perform better, the red up there, than using the regret preference model on it. So the takeaway for this second part is that when a preference model generates a data set, that same model is the one that produces the most aligned reward functions or the most performant reward functions. And so an interpretation of this is that the correctness of the preference model affects alignment. So this is really like one of the key takeaways of the talk.
So
Yes.
what is the
So it's this thing that I was hoping to not have to define. It's across these 100 MVPs, in what percentage of them is the learned policy, or really the policy that's optimal for the learned reward, is the performance near optimal with respect to the real reward. So it's a little complicated. That's why I was hoping to just like leave it at near optimal. And the way we do that, because these are different MVPs, the returns have to be standardized. We don't want to just like lump all the returns together. And so we do a linear transformation of the returns so that a return of 1 is optimal. A return of 0 is what a uniformly random policy would get. And so that way we standardize the returns for all 100 MVPs, and we define near optimal to be 0.9 or higher.
How do you define true?
So for synthetic preferences, it's defined by the random creation of these MDPs. So there's a reward function that is sampled as part of creating each MDP, each grid world. And then that reward function is going to dictate preferences in 2 different ways, depending on the 2 preference models. Does that make sense?
Sparse reward here?
What's that?
Are we assuming a sparse reward here?
Well, technically, yes. I don't think sparsity versus density is. Oh, yeah. The question was whether we're assuming sparse reward. So sparsity versus density doesn't really come into play here because we're not concerned with shaping. Really, we define a ground truth reward function, whether it's sparse or not. Like, I don't know what you would call a, let's just take like, I don't know, here. So this one, running into a sheep is like a failure and a termination. Getting to the destination is a success. Is that sparse? Is it not? Like, you can get lots of negative feedback by running into a sheep in a short horizon, but to really get to the goal and act optimally, it's a longer horizon. So I guess maybe it's sparse, maybe it's not, depending on the MVP. Okay. Yeah.
Is there a reason why with the increasing number of preferences, the proportion of MVPs that are optimal reduces for the case where you learn that regret benefit created by possible?
We didn't look into that one. It was the least interesting of the 4 because we don't think this is a strong descriptive model of people. But we will look into the second half of the talk, depending on time. We'll be looking into where regret is the generator, but partial return is assumed. That's pretty interesting. Yeah. So let me just jump forward. We very carefully gathered a data set of human preferences. This is our elicitation interface. Again, it's a little washed out here. And we carefully trained people beforehand and taught them that the reward was aligned with, we taught them in terms of dollars. There's like a robotaxi delivery task. So we avoided jargon. And with this data set, we look at the cross entropy loss, which relates to likelihood of this human data set under the 2 models. So here's an uninformed one, here's partial return, and here's regret. So we see that we get the best loss for the regret preference model. This is where they get the true reward. So we're letting them have the true reward, and then we want to see how likely the human data set is. We also learn with this data set where so we've got the human data set, and we're going to learn with each of the 2 models. And what we see, so this is similar to what we saw before, except so we have 1,812 preferences, and the x-axis is a little funky. So there's only one sample here, which is the full 1812. But then we cut it into 2 randomly, 2 partitions. So here there's 2 samples. Here we cut it into 5 partitions, so we have 5 samples, and so on up to 100 samples. And so there's the possible outcomes are a little more trustworthy over here than here, where there's less samples. But what we see is the regret preference model with lower samples does better. With small amount of samples, we have like about twice as frequent near optimal behavior. But then we do see in this task that both models do end up getting to optimal behavior. So to summarize this portion of the talk, we've critiqued the partial return preference model as a poor model for humans, proposed the regret preference model instead. And then we found, at least to the extent of our investigation, that the preference model, regret preference model, is superior by intuition, self-reflection. Either you agree with me or not, but for me, I think that's true. By theory, in terms of reward identifiability, it's descriptive power in terms of the likelihood of the human data set, and then its performance on learned reward functions, both with human preferences and synthetic ones. And then again, the biggest thing that I hope people will take away is that the choice of preference model matters. Whether you think the regret preference model is like the golden standard model, I don't think it is necessarily. I think it's an improvement, and it has some nice theoretical properties. But possibly the more lasting impact is that we really should not be ignoring this preference model, which is how we infer from people's preferences what's the hidden state, meaning the reward function in their minds. Okay, so some limitations. We talked about efficiently estimating regret, definitely a challenge if you're learning reward function. I mentioned the prescriptive methods that can nudge people towards one preference model or another. And then the partial return preference model has had considerable success. And if the regret preference model is actually correct, how do we explain that success of the partial return preference model? So the remainder of the talk will be answering that question. And that brings me to more recent work that we have under review. And the author list is similar, but we've now added Sigi Adolf-Gitterson and Anka Durgan. All right, so just repeating this, the question we're asking is, if the partial return model is so bad, little hyperbole there, why has using it performed so well in practice? And the outline for this is a different way to put this is, if regret is driving preferences, but the dominant model is assumed, what are the consequences? And one way I'll explain this, but a way of framing that is that people are using this optimal advantage function as the reward function. So I'm going to talk about what the consequences are when A star is known exactly for the ground truth reward function. And I'm just going to, for shortness, I'm going to say A star instead of optimal advantage function. Also when it's approximated, so it has some approximation error. And then reframing RLHF for LLMs. I might skip some of the middle content to make sure I get to the stuff at the end. So going back to the preference models here.
Brad, people should be keeping in mind that the RLHF for ChatGPT is using the partial return model.
Yeah.
So that's sort of the motivation for this part.
Yeah, that's
what
right.
is the dominant model?
Nominally, they think they're using the partial return preference model.
What is dominant model?
Oh, sorry, dominant meaning that is the one that almost everybody's been using. So partial return,
Including ChatGPT.
yeah, maybe predominant would be better.
So do you conjecture that they would do better if they use the regret one?
We could talk very loosely, or I could get into the real content. The answer is no. Actually, the answer is that the framing changes and the algorithm doesn't change. So we get rid of some what I would consider ugliness of the algorithm that is actually, I think, quite confusing to people as well. So you end up with the exact same algorithm, but with a different reason for the algorithm.
I see.
Okay, so again, this is the general family of preference models, and this statistic is the sum of reward. Again, I'm ignoring discounting just for simplicity. The sum of reward in one segment minus that of the other segment, that's the partial return preference model. And for regret, it looks pretty similar, except instead of the reward, you got this optimal advantage A star. So we could unify these as just saying there's some agnostic function G where we're not saying what it is, but the algorithm that's used to learn R could be used to learn A star if you just interpret G as A star instead. So these are now that I've mentioned that, we've covered 3 algorithms now. The predominant algorithm is the first one, where the partial return preference model is assumed. This G learning is done, and the output G is assumed to be a reward function. Policy improvement is done to get an approximately optimal policy, or at least they hope so. The algorithm that I just talked in length about that's new is where you assume the regret preference model. You learn a reward function from that policy improvement to get a policy. And then the one that I just briefly mentioned is where you assume regret preferences, you do the exact same algorithm, G-learning, but you get an A-star algorithm. And then you don't have to do policy improvement. You can just greedily maximize A-star because whatever action maximizes it, if you ignore approximation error, whatever action maximizes it is an optimal action. So these are the three algorithms that I mentioned so far, but what we're going to focus on is the algorithm that everybody's been using, except what happens if we assume they're wrong and the regret preference model is what's driving preferences, but they are still assuming the output, which is an A-star. This is totally washed out. You can still see the A-star here on my computer. But they're going to use the A-star as rewards. And then we're going to compare that to just treating it as an A-star and greedily maximizing it as the baseline. We're working on another paper focusing on this as an algorithm, but we're just going to use it as a baseline here. And I'm going to name these greedy A-star, just greedily maximizing the A-star. This hat just, again, means that's the approximated version. I apologize for the hat differences here. And then, and I'll name this one greedy Q-star, where this complicated reward subscript just signifies that the reward is actually the optimal advantage. Okay, so let's see. I'm gonna just do, yeah, okay. So I'm gonna talk first about where we actually have A-star, no approximation error. And there's some surprisingly positive properties here, which might explain some of the success so far. So it turns out that if you have the true A-star for some ground truth reward function, and you treat it, this A-star as a reward function, that you end up with the same set of optimal policies. And the quick intuition here, which I don't expect everyone to follow, but the quick intuition here is that since the max in every state, A-star is 0, and optimal actions have a A-star output of 0, then any optimal trajectory will have a return of 0. Whereas any suboptimal trajectory will have a return that's negative because it'll have some action that has some negative A-star. And so basically taking actions that will give you the highest return are the same as taking the actions that give you the highest A-star. So another thing is that the reward ends up being highly shaped. In Andrew Ng et al.'s paper on potential-based shaping, they suggest a very potent form of shaping where the potential function is defined to be the state value, the optimal state, the optimal state function. I can't talk about optimal state value function. And what we find is that with a little bit of algebra, their definition of the potential function is the same as using reward that is the optimal advantage. And so here what we're saying is that if preferences are from regret, and people are using the partial return preference model mistakenly, they end up with this highly shaped reward function that is sort of the ideal of what Andrew Ng et al. Said to use, but that's without approximation error in the learning. And then, so one downside here is that this policy improvement, using it as reward, wastes computation and possibly sampling environment. Because if you have the A-star, then why treat it as reward? You can just greedily maximize it and get the same consequence, the same policy. So I'm gonna, for time, I'm gonna skip this. So we do find challenges once we add approximation error when learning A-star and then using it as reward. And then we find it's still highly shaped, so that still supports this idea that this may have been actually a fairly good overall outcome if people are incorrectly using a learned optimal advantage function as reward. But I'm going to skip over the details there to get to the LLM part. And so from the InstructGPT paper, which ChatGPT is directly based on, by Ouyang et al. I hope I'm saying their name right. This is part of their main illustration for how they do fine tuning. And just to map some of it to what I've talked about so far, what they're calling a reward model is our hat. And they're assuming the partial return preference model, and segment length is 1. And this same approach at a high level is being used for a lot of different other influential language models. So let's look at the multi-turn language problem. from an RL perspective. So I guess first, from the language model perspective, you got a human prompt, language model's response, and there's lots of tokens in each. Then another prompt, another response, prompt response, and so on. If we frame this reinforcement learning framing, then there's an observation the LM agent gets. It takes an action, another observation, an action, and so on. And so you can express this in the sort of canonical way that we do for reinforcement learning, as the human is the environment and the agent is receiving prompts as observations and taking responses as actions. There would be a reward for each observation and action. And the normal way to do this in reinforcement learning is that if you want to evaluate the quality of an action, you look at the sum of reward from that point onwards, more specifically the expected sum of rewards, maybe with some discounting. But let's see what's actually being done here.
Is the human rating the conversation? Is that where the reward is?
Yeah. If I had more time, I would have put a slide in to show the actual interface. But basically, the normal thing is a history of dialogue is shown, and then let's just take InstructGPT for example, and then the model generates, I think, 3 to 7 responses, and those are ranked, which can be turned into pairwise preferences, which actually are turned into pairwise preferences. And the interface very much is saying like which one is better. It's not something that really corresponds to which one has more reward, but really like which one is better, which I think corresponds to the regret formulation of which one's closer to optimal. But yeah, so let's look at what's actually happening. When these LLMs are fine-tuned with RLHF, the reward is used in a quote bandit environment. That's a quote from the Oyang paper. But that's very strange from an RL perspective because this is not a bandit problem. This is a sequential problem. And I think that's led to a lot of confusion. And one way to think about a bandit environment is that you're setting gamma to 0. And that means that you only care about the immediate reward, not about any future reward. And I'm going to just get on my high horse and my judgmental high horse for a second. I think that using this reward function as sequential task as a bandit reward function is counterintuitive and unexplained, and I think it's responsible for confusing a lot of people. I will say that I did something very similar with my dissertation work, where we use a gamma equals 0, but we explained that a lot. We put a lot of thought into why that was a good choice. So let's just think about so they're assuming a partial return preference model, but what if we assume that the learned G is actually a regret preference model instead? So under the partial return preference model, in this strange assumption that gamma equals 0, and like if I had more time, I go into it, it's actually an arbitrary assumption. What happens is the optimal policy is this argmax of Q star, which expands out to this, but gamma is 0, so this goes away. So then it's just argmax of the immediate reward, which is argmax of this G function. If you use the regret preference model instead, you don't have to assume anything about the gamma hyperparameter. And you end up with the same thing. The optimal policy is argmax of the A star function, which is the argmax of the G function. So you end up with the exact same algorithm without making this arbitrary assumption about gamma equals 0, or doing this confusing thing of using a reward function in a bandit way in a sequential task. So I think I guess I'm basically at the end. So just to review what I've said already here. The proposal here is that what is learned during RLHF for LLMs is better thought of as an approximation of A star than a reward. And the reasons for this are that one, just the regret preference model is more supported. Nobody had really looked at the partial return preference model. So it's not like I have some competitor who's saying, no, let's do the partial return preference model is better. That's just the assumed part of a lot of papers. Also, it explains what I found previously hard to justify, the treatment of the sequential task as a bandit problem, because treating it as a bandit problem is a way to force R to act like an A star. So it's a way of getting the regret preference model maybe without realizing it. And it also removes this other specification regarding the discount factor gamma. And then you might ask, well, what's the consequence of all this? Like, why does it matter to reframe something without changing the algorithm? One, just as scientists, I hope that we care about having a better understanding of what underlies our algorithms. But also, if you do want reward that will be added over multiple turns, so if you do want to have some interaction where there's a goal in the interaction, and so you're going to add reward to try to tune for that goal, then this is going to suggest a different algorithm, which is the algorithm from the first half of the talk, using the regret preference model, which does have that challenge that it involves solving MVPs in the inner loop or approximating that. But that's a nice challenge. You know, we like research challenges. So just to summarize, very, very high level, using A star as a reward function is less harmful than expected. It's still not advised because you can just use A star directly as A star. And then also I propose a new framing of RLHF for LLMs, which is that the fine tuning is optimizing to an approximation of A star, not to a reward function. So I'll just leave with these this kind of quick summary and then the QR codes, and I can take any questions. Thank you for listening.
We have some time for questions. Go ahead. And remember to repeat the questions.
Yeah, thank you.
Two questions. Regarding the LLM thing that you mentioned, I'm a little bit confused because in the first part of the talk, when you're saying that you're optimizing identity plate from scratch, right? But in LLMs, it's like a fine tuning, which is you have a regret based on the cross entropy automated block, and on the top of it, you're again aligning it with some other RLHF, like human feedback. So, my question to you is, why do you think that if a model is trained with like trillions of data and it is already already have a good perplexity in language model complexity, why do you think that adding extra human person on the top of it is more like? So isn't that they don't know which, they have a set of answers and they don't know which one to choose? And the second question is in your first part of the.
Can I stop you? I'm very bad at 2 questions. My memory is not that good.
Repeat it.
Yeah, so yeah, see if I can remember the first question. When you said second question, the first one was just like, wow. You started by saying that for LLM fine tuning, there's already a policy that you start from. And that is an important distinction. It doesn't change anything necessarily that I said. I just kind of skirted over that. You could use everything in the first half of the talk, where you also maybe have some starting policy and you minimize. You also have like a KL divergence loss term that keeps you from moving too far from the starting policy while also optimizing to your learning reward function. So that's really like, I think there's good questions about whether these techniques are best starting from scratch or best adding on top of some policy. Maybe it just depends on what you have to start with.
No, but it is that it's already in the optimal point.
So, but yeah, your real question was about why fine tune at all. So that is something I don't. I'll tell you my answer. I don't think that I'm like my expertise on that is not perfect, but my sense is that there's one stage where the LLM is trained on like just roughly all the data, all the text online. And that includes hate speech, incorrect answers, all sorts of things you don't want it to emulate, including things that are good for humans to do, but bad for LLMs to do, like wanting self-preservation. So then you have this demonstration step, and I'm just talking about ChatGPT. I think it's a little bit different for some of the others, but you have this demonstration step, which helps, I think, fine-tune that out a bit more. But I think the last step, so there might be a couple of things going on. My sense is that, sort of like you hinted, that the LLM can already produce good answers. It's just also got a high probability of producing bad answers. And so the fine tuning, probably both by demonstration and by preferences, is my guess is not teaching new skills. It's a hand wavy thing to say, but it's not teaching new skills so much as telling the LLM of all the skills it has, which ones to actually exhibit. But I'm not like an expert on that part of it.
Maybe we should rotate questions before going back.
Yeah.
So there's some studies showing that LLMs are getting worse at solving things over time. Like like a couple months have passed and like they can't do things as well as they used to be able to do. And I didn't read the details about why, but I'm just wondering if you think it's connection here, or if you what is your take on that?
Yeah, I don't know. I've heard that too, but I haven't looked into it. I'm definitely curious about it. If anyone else knows anything more details, you could speak.
If you're
and
talking about
share.
the coding thing, that experiment is completely wrong.
Okay.
Oh, really?
The
So
99%
to 2%, they just didn't parse the output correctly because it changed the formatting of it.
I'm just looking at something from Stanford, but I don't.
Yeah, that Stanford paper is completely
Got it,
wrong.
okay.
Yeah.
Not up to date then.
Right?
So Brad, on your last point, I think a lot of it's called ChatGPT and dialogue, natural language already, they focus on like sort of chat dialogue, where it's just like, I want a nice response immediately, and so you keep the person talking. Whereas there's task-based dialogue, where there's actually, I want to accomplish some goal in the end, I want to, plan a trip to go to a conference or something, and
Yeah.
I need multi-turn interaction to eventually get to a state. I think all this RLHF training has been done in this sort of chat environment, right? And not in the sort of task-based dialogue environment where I have a long-term goal that the thing's actually trying to accomplish. And humans are giving these feedback based on whether it's actually moving towards that long-term goal. I mean, I'm assuming you agree with me.
Yeah, I
We
do.
need to build systems that are more built to have longer dialogue that actually have an end goal rather than just chat.
But
Yeah.
chat is also sequential, right? I mean,
Well, yeah, but
But it's not trained in a sequential way.
That's right.
Matters.
right.
Yeah. I will say, I agree with you. I do think there's extra safety concerns. The more you have an agent pursuing long-term reward, the more, I think, more likely it is to find some very undesirable way of getting that reward. Whereas the preferences, I think, are very akin to demonstrations right now. We're saying, in this state, it's better to do this than to do that. I think there's less room for I don't like the word exploitation because it blames the LLM, but
Utilization.
what's that?
Utilization.
Sure, yeah, and undesirable utilization. But yeah, so I think as we move to actual using real reward for generative models, we definitely want to think about safety carefully.
So do you think it's possible if you just instructed people very carefully, do not pay attention to anything, to any possible future that could happen after this segment, only pay attention to what's happening in the segment, is it good or not? Could you get people to model real reward?
You mean, could you get them to follow the partial return preference model?
Yeah, can you?
That'd be interesting. It sounds like a very bad interface, but it'd be an interesting experiment, to see whether. I mean, part of the problem with, even for me, for thinking about the partial return preference model with large language models is it's hard for me to even think what a reward function would be for a general language problem. Like, it's one thing if you have a task like Ray was talking about.
Mhm.
Didn't that backflip, like the paper with the backflip and the
Yeah,
photo also involve a component for sort of confidence or curiosity? Basically, if it was getting rewards, if it saw transitions it was uncertain about, it would tend to give more examples like that to the user.
I think so. So they did have an active learning component.
Basically,
I think
I'm
they
wondering-
used a ensemble method and would learn a bunch of reward functions from subsets of the data, and then they found areas of disagreement and preferred to give segment pairs where there's disagreement.
Well, the significance of the actual question is, if you're targeting areas of uncertainty or whatever, does that maybe help you get a robust reward function, even if that makes up for the fact that it's not really a good model of anything? Because you're targeting areas that matter the most, you sometimes you trick the model into learning good behavior, even if in a global sense it has these weaknesses you've already identified.
Yeah, I mean, so with the identifiability results, no matter what question you ask, the identifiability results rely on, we're assuming infinite exhaustive data. So asking about areas of uncertainty doesn't necessarily address the identifiability weaknesses. Yeah, beyond that though, I'm not sure.
Did you have something, Scott?
Oh, I was just gonna say, within a language model, you can have tasks help me solve this, coding problem or this math problem, right?
Yeah.
But then is the reward you want to provide, only provide reward after it, if and when it solves the problem, or do you want to ask the human for partial rewards along the way?
Yeah, I think there's still this question, you can identify the task, but then there's all these, these conversations about extraneous reward, where you ask your robot to get you a drink out of the fridge and do it as fast as possible. So your reward function is -1 per second until it gives you the drink. So it finds the shortest path through your wall. So there's hidden parts of the reward function that you really care about.
Yeah.
And so, yeah, I think that's where the safety questions come in. Is it just that we minimize scale divergence from the existing LLMs that we've carefully fine-tuned? And you could also see this being particularly bad in a profit-driven scenario where you ask the LLM to like make a sale.
Mhm.
I could easily imagine it exploiting people in some way to make a sale.
Maybe we should, in the interest of time, thank the speaker one more time and take up the.